Okay, final question, question 10. This bit's quite nice. It's a pleasure to do this bit. The 6 marker that follows in a second is a bit of a beast, but compared to what you've just done, you should be fine. So an electric kettle contains 1.41 kilograms. Just going to check the specific heat capacity. Yep. Goes from 25 to 100, so that's a change of 75 degrees C. Yep, that's in degrees C. I haven't got any kelvins or nothing like that, and calculate the amount of thermal energy. So Q equals mc delta T. The tricky bit is it wants us to go to an appropriate number of significant figures. So we'll go to 2 significant figures. But we'll look at the size of the number first. So if it's a little number, we'll increase the significant figures. If it's a big number, we'll go to 2. So 1.41 times 4,200 times 75 equals 444,150. We're not going to worry about that little bit there. Equals 440,000 joules. Okay, next one. The kettle is switched on and the water continues to boil. So imagine, obviously it's an open kettle at the moment. We're now going to have some water will escape, and that will be Q equals ml for that. We've got to change the state. So after a while, the mass in the kettle decreased to 1.21. So 1.41, take away 1.21, we know 0.20 kilograms change state. The thermal energy was 450,000. Calculate the specific latent heat of vaporization. So we're going to need a my quirky llama, and we want L, and we want to use that. And let's just check that's in kilos, that's in joules. Perfect. So we're good to go. We've checked the units. We've done any unit changes. So the mass of evaporated water is 0.20. Put that all in. Comes to 2.25 million. I'll just write that straight in. Okay, this next one's tricky as a 6 marker. So we can see we've got an aluminium block there, and it's in boiling water. So let's say it's 100 degrees C. But we're going to be certain we're going to take the temperature of that at the start. We're going to take the temperature at this beaker at the start, and then we're going to leave this, let's leave it at least 5 minutes so that it can get up to temperature, so that it can equilibrate. Once that's ready, we're going to move that super quickly so that we don't lose any thermal energy, and we're going to dunk it into here. We will then take the temperature, so we've taken the temperature at the start, we will then take the temperature at the end, and we'll work out delta T. After that, we're going to assume that all of the heat energy or thermal energy from this block has gone into the water. So we'll then stir it round and round and round, and then we're good to go. Well, the next part now is, well, we've worked out delta T. We know C for water. So if I just write in here, we know Q equals mc delta T. And I can assume all the energy that went into the water came from the aluminium block. So if we just quickly go through this, we know that value, C is 4,200. We know the change in temperature, which is my temperature at the start and temperature at the end once I've stirred it. So we know that. What we don't know is the mass. So if I just get rid of all my squiggles now, well, what I'm going to do is take the aluminium block out, put that on some digital scales. We've got to dry it in between. So I pat it with a paper towel or measure the mass at the start before I get it wet. Then, now that's taken out, I can find out the mass of the beaker plus the water, tip the water away, and then I've got the mass of the beaker. And then taking those two away, I've got the mass of the water, and that's now that bit. So once I've got that, I've worked out the Q for water, and we're going to say that's equivalent to Q for aluminium, and now we want to work out C for aluminium. So this is really tricky in terms of the steps. So C is going to equal whatever the energy was that we put into the water, divided by the mass of the water, and now for the tricky part. And then it's going to be this temperature and that temperature, and we're going to find out the change in that, and that is tricky to word. Okay, so we want the temperature of the first set of water, and then the second once it's warmed up. Okay, so we've got 2 delta T's here. This one here, where I do the start and the end to find out for the water, and these two so I can find out the temperature change of that block. So it's tricky. I'm going to rub this all off, and then the model answer is going to come in, and if there's any problems, come and see me. And I definitely suggest you make a revision card on this and go over and over and over it, because it's not an easy question. So if I just get rid of all my doodlings, and then I'll try to highlight the bits as they go through. Gosh, this deleting is taking forever. Here we go. I've got rid of most of it. So the first part is measure the temperature of the boiling water and the cold water with a thermometer. Ba-dum, ba-dum. Allow time for the block to get to the right temperature. Tick. Let's draw a little stop clock. And let's give it 5 minutes. When we're ready, remove that, dunk it, stir it. So remove the hot block as quickly as possible to avoid thermal energy losses. Stir the water and take the temperature again. So I'm now going to say temperature 1, temperature 2, temperature 3. Calculate the temperature change of the cold water. So that's T3 minus T2. Hoping this is making sense. Remove the block. So the block was in there. Let's take that out, dry it, and find out the mass of the block. Next part. Find the mass of the beaker and the water, then empty the water, subtract the values for the mass of the water. Now we've got everything. We know Q for the amount for the water equals MC delta T. That's the mass of whatever I've got there, times specific heat capacity of water, times T3 minus T2. There we go. And feel free to label your diagram as well. This is a tricky question. The last part now. Well, we can assume all of the energy that went into the water came from the aluminium block. So C for the aluminium block is Q water divided by the mass of the aluminium, and you'll see I've purposely left this one out. I don't want you thinking like usual I've missed something out. Multiplied by the delta T, but be specific. So I can now go to this and explain it by saying, and that's T2 minus T1, or the temperature of the hot minus the warm, depending on how you want to word it. And that's that really tricky 6 marker done. And good luck in learning that.